Good morning. Okay, we continue with the harmonic excitation of S2F systems. With one example, we continue. In this example, we deal with an unbalanced, rotating unbalanced system when an exhaust fan of mass 380 kg is supported on a spring with negligible damping. So we don't have damping. The resulting static deflection is found to be 45 millimeter. If the fan has a rotating unbalance of 0.15 parameter, find the amplitude of vibration at 1750 RPM, and part B, the force transmitted to the ground at this speed. So for part A, we need to calculate the amplitude of vibration when the frequency of the motion is 1750 RPM. You should convert it into the radian per second to obtain the frequency of the rotation for the rotating unbalance. And from the given data, we can calculate the natural frequency of the system. Here we have the mass of the system, and the static deflection is 45 millimeter, and we have also the mass, so we can calculate the stiffness because the static deflection is due to the weight of the system, which is 380 times by g, which is the gravity acceleration, and it's equal to 9.8. And the deflection is 45 millimeter. We should convert it into meter, and then we can calculate the stiffness of the system. So the static deflection, which is 45 millimeter divided by 1000, we should convert it into meter. It's equal to the weight of the system divided by K. Okay, because we know that F is equal to K times by X. X is the deflection, K is the stiffness, and F is the weight when we deal with the static deflection of a system. So from this equation, we can calculate the stiffness of this system, and it's about 82 kilonewton per meter, or 83 kilonewton per meter, in fact. Then we can calculate the natural frequency of the system, which is equal to the square root of K divided by M, the stiffness divided by mass, and it's equal to 14.76 radian per second. And as I told you, we can calculate the frequency of the rotation from this value of the RPM. We should convert it into radian per second by multiplying by 2 pi and divided by 60. And this is 183.2 radian per second, the frequency of the rotation for the fan. Now we can calculate the frequency ratio, which is the ratio of omega to the omega n, and it's equal to 12.41. As you can see, the omega is more than omega n. It's about 12 times by omega n, the natural frequency of the system. Now we can calculate the amplitude of vibration or amplitude of the response from the formula. We need to substitute into this equation. We know that the rotating unbalance is 0.15 kilogram meter. If you attention here, pay attention to the unit of this rotating unbalance, you can see that this is kilogram meter. It means that this is M times by E. This term which is the mass multiplied by the radius of the mass. If you remember from the yesterday lectures, the rotating unbalance is equal to the mass of the unbalancing particle multiplied by its radius of the rotation. Here, because the unit is kilogram meter, we can find out that this 0.15 in fact is equal to m times by a. If it was, for example, rotating unbalance, the mass was 0.15 kilogram, it means that the mass of the particle is 0.15, and also we need another data, which is the radius of the rotation. So here, because this is kilogram meter, it means that this is the mass times by its radius of rotation. So instead of m times by e, we substitute 0.15. R, which is the frequency ratio, it's equal to 12.41. M is the mass of the system, which is 380, and Kasai, which is the damping ratio, is 0, because in this system the damping is negligible. So we substitute and simplify, and finally we can find the amplitude of the response subjected to this condition. So the next step, in the next section, we need to calculate the force transmitted to the ground at this speed. We calculated the displacement x, and we know that the force transmitted in rotating unbalance is equal to k times by x plus c times by x dot, which here c is 0 because the damping is negligible. So the force transmitted is equal to k times by x. Here, this is the maximum value for x, and k, which is calculated here, this is the k. So we can calculate the transmitted force. So, and it's equal to 32.91 Newton. This is the force transmitted to the ground due to this rotating unbalance on this system. Okay, any question? Is it clear? Okay. Next example is a centrifugal pump rating 600 Newton and operating at 1000 RPM is mounted on 6 springs of a stiffness 6000 Newton per meter each. Find the maximum permissible unbalance in order to limit the steady state deflection to 5 millimeter peak to peak. So the amplitude of the response, the maximum amplitude of the response is 5 millimeter divided by 2, because this is 5 millimeter peak to peak. So the amplitude is 5 divided by 2. If we assume that, for example, this is the response, the peak to peak is 5 millimeters. So this length is 5. And from here, we can conclude that this is the amplitude of the response, which is 5 divided by 2. So we have the amplitude, or x, which is 2.5 millimeter, or 5 divided by 2. The weight of the system is 600 Newton. And also the omega is 1000 RPM, which we should convert it into radian per second. We have the stiffness of the system. So the stiffness of this system is 6 springs with the stiffness 6000 each. So the stiffness is equal to 6 times by 6000, which is 36 kilonewton per meter. We want to find the maximum permissible unbalance in order to limit this motion. And so unbalance is in fact m times by e. We want to calculate this m times by e in this example. So We can calculate the frequency ratio. We have omega, which is 1000 RPM. We should convert it into radian per second by multiplying by 2 pi and divided it by 60. And also we have the stiffness, as I told you, it's 36 kilonewton per meter. So we can calculate omega n as well, which is a square root of k divided by m, and m is 600 divided by g, because this is the weighting. You can see the unit is Newton. So W is equal to 600, and we know that W is equal to mg. So from here we can conclude that m is equal to 600 divided by g. And now we have the omega n in radian per second, and we can calculate r, which is the frequency ratio, and it's equal to omega divided by omega n, and it's equal to 4.31. So you can see r is more than 1, so we are far from the resonance. Now we need to calculate the x, or they find the relation between the amplitude of the response and the unbalanced mass. So here again, we don't have damping in this problem. When we don't have damping, psi is equal to 0, we can substitute here and find a relation between x and me. As you can see, x is equal to mer squared divided by the total mass of the system multiplied by the absolute of 1 minus r squared. R is obtained here. We have the maximum x, which is 5 divided by 2. Of course, millimeter, we should convert it into meter. We have the mass, which is 600 divided by g. And we can substitute and calculate ME, the maximum permissible imbalance, to achieve a value of 2.5 millimeter for x. So ME can be obtained from this equation, and it's equal to 0.144 kilogram meter. So this time the unknown parameter is ME, but in previous example the unknown parameters was, I think, x, the amplitude of the response, but here we need to calculate the permissible unbalance in the system. Any question? Okay. Okay, the next concept is the forced vibration of a system with column damping. If we extract the equation of motion, we have this term. As you can see, this part is exactly the same as the free vibration, and only we have one non-homogeneous term, which is due to the external force F naught sine omega t. Here in this chapter, we assume only the harmonic excitation again. So we assume that, for example, the external force is a function of time in the form of sine harmonics. So this is the general form of the equation of motion. As you can see, we have a nonlinear equation because we have plus minus mu n. So the solution for this problem is a little difficult. I mean, you need to obtain the response for a specific half waves, half cycles, and it's a very long and complicated procedure. But generally, when we deal with the force vibration of column damping systems, we will have two main options. The first one is when the friction damping is more than the amplitude of the external force. So in this case, the motion will be discontinuous. For example, if you assume, this is a system with column damping, and here we have a friction. On this surface, we have, for example, mu, and this system is subjected to a force Ft. When the friction force is more than Ft, this system will be remain at rest, or if it had a motion, the motion will be discontinuous. It will, for example, comes to the right, it will be stopped, and again, when the force in the spring and the force in external force direction was in the same direction, maybe the mass start to move, but as soon as the direction of the force in the spring change, this mass will be stopped again, and the motion will be discontinuous. So in this case, we cannot solve the equation of motion. At least we cannot find an arbitrary form for the response, and we cannot find a continuous form for the x and for the response. So this case is not studied in this part, in this chapter. And the second case, when the dry friction damping force is less than the amplitude of the external force, and it's small in comparison with the amplitude of the external force. In this case, because the external force is harmonic, we can assume that the response x is, it can be estimated as a harmonic because the external force is harmonic. So we can find an equivalent viscous damping for this system using the method explained in previous section, and we can find an equation with the equivalent coefficient of viscous damping and extract a new form for the equation of motion, and then we can solve that equation to find an approximation for x. So in this case, in fact, we only estimate the response, but this estimation, when f is more than mu n, and you will see that how much should be this f and how much should be the friction force. In the next slide, I will explain, and according to the mathematical equation, you will see that what is the restriction and what is the limitation for mu n to use this approximation. And for this boundary of mu n, we can use this assumption, and this estimation in engineering field is acceptable, and we can use this method to find the response of the system. So the second case will be studied here, and to find the equivalent viscous damping, we should use the energy dissipated equation. We know that in a system with dry friction or with a column damping, the energy dissipated in a full cycle is 4 mu times by nx. And for a system with viscous damping, the energy dissipated in each cycle is pi times by c times by omega x squared. Of course, all of these relations are only for the harmonic excitation and harmonic response, okay, with these assumptions. So this equivalent C, or the equivalent viscous damping constant, can be obtained from this equation, which is equal to 4 mu nx divided by pi omega x squared. So from here, we can obtain the equivalent damping constant, as you can see here. And you see this is a function of x. I mean, when you want to solve this equation and you substitute into the main equation, you will see that the coefficient in your equation of motion is a function of the response. So we can use the equation of motion and find the formula for the particular response in this form, because this x in fact is the amplitude of the particular response. So we can substitute into the equation to simplify and extract a relation between the amplitude of the response and the external force. So here you can see, if we assume C equivalent is the equivalent coefficient of x dot in the equation of motion, we have K and M, and omega, which is the frequency of the excitation. So we can substitute here, and also we can write this equation in the form of the damping ratio and frequency ratio, and simplify this equation for psi equivalent, which is the frequency ratio, the damping ratio equivalent, and it's a function of C equi. It means this is the equivalent damping ratio in the system. So we can find psi equivalent as a function of the frequency, as you can see, and also the amplitude of the response. Then you can substitute here, and if you simplify this equation, you can extract this relation between the amplitude of the response which is subjected to the external force with amplitude F naught, the stiffness K. Mu is the coefficient of friction between the mass and the surface. N is the normal force between the surface and mass. And omega is the frequency of the excitation, and omega n is the frequency of the system, which is the square root of K divided by M. And also we can obtain the angle phase, which is tangent inverse of this term. And you can see that angle phase is again a function of mu, the coefficient of friction, the normal force between the mass and the surface. F naught, which is the amplitude of the external force, the harmonic external force. Now we can substitute and we can obtain the amplitude and the angle phase for this xpt. So again, I should mention that this response is only an approximation for your response when we have the harmonic excitation. If the excitation was not harmonic, we cannot use these equations, okay? So this is only valid for the harmonic excitation, and when the external force is more than the friction force. And here you can see in this phrase, this term must be positive to have a real value for the amplitude. What does it mean? It means this term must be positive. 1 minus this parenthesis squared must be positive. And from here, we can find a relation between mu n, which is the friction force, and F naught, which is the amplitude of the external force. So from this term, we can conclude this solution is valid only for small friction force when this term is positive, or F naught divided by mu n must be more than 4 divided by pi. So if you want to check the validity of your results, you can check this equation. If the ratio of F naught, which F naught is the amplitude of the external force, the harmonic external force, to the mu times by n, which mu n is the friction force, was more than 4 divided by pi, then we can conclude that this equation is correct, or this assumption is correct, and we can use this equation for the response of the system. This is the amplitude, this term is the angle phase, and this is the particular response, or the steady state response of your system. So this is the total procedure. So in the first step, we assume that we can find an equivalent viscous damping system for the system with column damping. Then we solve the equation of motion, and because the equivalent damping constant was a function of the amplitude of the response, we substitute into the general form of the response. Then we simplify and again solve this equation for x and extract the x, the amplitude, from here, and here this is the amplitude of the response. And also we solve it for the angle phase. So this is the approximation solution with these conditions. Under these conditions, when f naught to the mu n is more than 4 divided by pi, we can approximate the response in this form. Any question? Is it clear? No questions so far? Okay. Okay, we continue with one example. A Scotch yoke mechanism operating at 30 radian per second is used to provide base excitation to a block as shown below. The block has a mass of 1.5 kilogram and is connected to the Scotch yoke through a spring of a stiffness 500 Newton per meter. The coefficient of friction between the block and the surface is 0.13. Approximate the steady state amplitude of the block. So here we deal with a system with column damping. As you can see, the coefficient of friction is 0.13. So we can check first the condition. The condition of F naught divided by mu n must be more than 4 divided by pi. Also, here we have one spring with a stiffness 500 Newton per meter. This is the spring. The force in this spring, if we want to calculate the force in this spring, we can assume that the displacement of this mass is x. And here we have another displacement. If we call it, for example, x of the yoke mechanism, we call it xy. So the force in this spring, F, is equal to K times by x minus xy. Okay, and xy is related to the motion of this arm, because when this arm is rotating, for example, in this direction, if it was rotating in clockwise direction with angular velocity of 30 radian per second, and we assume this angle is theta, this theta is equal to omega times by t. Yes, because the velocity is omega, the angular velocity is omega, so the position is theta is equal to omega times by t. It's similar to the equation of x is equal to vt. The position is equal to the velocity times by time. This is from dynamics. So theta, if we assume the name of this angle is theta, it's equal to omega times by t. If we assume it starts from 0 at omega is equal to 0, at t is equal to 0. So theta is equal to omega t. And at t is equal to, for example, 1 second, theta is equal to 30 radian. So this is the theta, the position. Now we can find the xy as a function of theta or omega t, and xy is equal to, this length is 10 centimeter. This is L. It's equal to L minus L times by sine theta or sine omega t. And then we can substitute here, and the force in the spring is equal to K times by x minus xy, or it can be according to the direction of the force for this spring, it can be equal to K times by xy minus x. Okay, so it can multiply by a negative when we change the direction. So this is the total procedure. We can extract the equation of motion for this system. So this is the equation of motion. Mx double dot. If you plot the free body diagram for this mass m, we will have, when this mass is going to the right, we will have one force due to the spring in this direction, and it's equal to K times by x minus L sine omega t, because as I told you, this xy, if we call it xy, is the different L minus L sine omega t. Here, if we assume that in the initial condition, when this mass is in the initial condition in vertical position, we can assume this is the initial position for the spring. So the deflection in the spring is equal to x minus L sine omega t, this term. Okay, so at each moment, the position of this point is equal to L sine omega t when it starts from this position by rotating in clockwise direction. At each moment, theta is equal to omega times by t. So the position of this point or this edge of the spring is equal to L sine omega t. So we can write the equation of motion mx double dot is equal plus k times by the deflection in the spring, which is x minus L sine omega t, plus minus mu n is equal to 0. There is no external force, and this term will appear as an external force in the equation of motion. Now we can write and form the equation of motion in the standard form, which mx double dot plus k, x is equal to the non-homogeneous term, which is mu n plus minus mu n plus k L sine omega t. Now we can check the conditions of the approximation solution. We know that the f naught in this case is equal to KL, or the coefficient of the non-homogeneous term, the amplitude of the non-homogeneous term. So we can check f naught divided by mu n is in fact KL divided by mu n. It's equal to 26.13, and it's more than 4 divided by pi. So we can use the assumption for the response, and we can use the approximation. So omega n, the frequency, the natural frequency of the system is square root of k divided by m, and the frequency of the motion, which is 30 radian per second here. So we can find the response for this system using the approximation, and it's equal to this equation from the previous slide. You know that the amplitude of the response when we use the approximation solution is equal to f naught divided by k, which here in this case f naught in fact is a function of the stiffness of this system. So this k will be cancelled out with the stiffness, and we can substitute and calculate the amplitude of the response. Okay, any question from this example? Is it clear?
Clear, sir.
Okay. The next concept is the force vibration with hysteresis damping. Again, we can assume an STF system with hysteresis damping subjected to the external force Ft, which Ft is a harmonic in the form of sine functions. The equation of motion for this system, again by using the equivalent viscous damping coefficient, you know from the previous section, you know that it's the equivalency is equal to beta k divided by omega plus kx is equal to f naught sine omega t. So we can solve this equation, and it's similar to the solution for the system with viscous damping. We have x double dot x dot x, but this time instead of c, we have this term, which is the equivalency and the external force. So we can substitute into the response. Instead of c, we will have beta k divided by omega, and we can obtain the amplitude of the response and also the angle phase. As you can see, the angle phase this time is a function of beta. It's not function of C, and we can substitute here and find the response. So this is again an approximation, and we are using some initial assumption. The first assumption in extracting the equivalent C was considering the harmonic response or the harmonic excitation. Okay, here because we have harmonic excitation, we can use this approximation to find the response for this system. Okay, again, similar to the viscous damping systems, we can plot the amplitude and also the angle phase for the frequency ratio. Here, there is two important difference between this graph and the graph for the system with viscous damping. If you compare them, the first case, if you look at the first graph here, their amplitude versus their frequency ratio, you can see that the amplitude ratio attains its maximum value, which is equal to F naught divided by K beta at the resonance. When omega is equal to 1, we can achieve to the maximum value for the amplitude of the response. While in the system with viscous damping, the maximum value of the amplitude happens before the resonance, and usually it happens when omega was less than omega n, or the frequency of the excitation was less than the frequency of the system. The second difference between the system with hysteresis damping and with viscous damping, if you compare the angle phase, you can see when omega is equal to 0 or R is equal to 0, here the angle phase starts from tangent inverse of beta. So in this case, you can see the response is not in the same phase of the excitation. While in the system with viscous damping, when omega was 0, the angle phase started from 0, and when omega was 0, the response was in phase with the excitation. So we can conclude that in the system with hysteresis damping, the response will never be in phase with the forcing or with the excitation. So this is the second conclusion that we can extract from these graphs. Okay, any question?
No, sir. No question.
Okay, thank you. We continue with one example. A load of 5,000 Newton resulted in a static displacement of 0.05 meter in a composite structure. A harmonic force of amplitude 1000 Newton is found to cause a resonant amplitude of 0.1 meter. Part A, we want to find the hysteresis damping constant of the structure. Part B, the energy dissipated per cycle at resonance. And part C, the steady state amplitude at 1/4 of the resonance frequency. It's easy. You only need to substitute into the equation. The part A, when we want to obtain the hysteresis damping constant, we have the weight, which is 5,000, the static deflection, which is 0.05. So we can easily obtain the stiffness, and it's equal to about 0.1 meganewton per meter. And then we can calculate the maximum value, because we have here, where is, yes, here the resonant amplitude is 0.1, and we know that the maximum amplitude will happen in the resonance, and it's equal to F naught divided by K beta from the previous slide. So F naught divided by K beta is equal to 0.1 meter here. So from here we can find the beta because we have F naught, we have K, and also we have the X, the amplitude. So we can easily find that beta is equal to 0.1. So this is the static damping constant, the beta. Part B, we need to calculate the energy dissipated per cycle. The energy dissipated is equal to pi c omega x squared, which c is the equivalency, and it's equal to beta times by k. So we can substitute and solve for delta E, or the energy dissipated per cycle, and it's equal to 314.15. And finally, in part C, we need to obtain the steady state amplitude at 1/4 of the resonant frequency. When the frequency ratio can be obtained from this term, the amplitude at 1/4 of the resonant frequency, it means that omega to the omega n is equal to 0.25. So this is the frequency ratio. And now we can substitute into the equation for the amplitude, and we can calculate the omega to the omega n is 0.25. So we substitute 0.25. We have the stiffness of the system, which is calculated here. We have the F naught, which is the amplitude of the external force. It's 1000. It's the given data. And also we calculated the beta in part A here. So we need only substitute here and calculate the maximum amplitude of the response. Okay, any question? If you don't have any question, we can wrap up this session, and after 10 minutes break, we can start the tutorial session.
Okay, sir.
Okay, thank you. So I will start about 10 minutes later, the tutorial session. Thank you.